everyone. This is Maurizio, editor-in-chief of Power Electronics News and Embedded.com. I am here at Electronica, showcasing in Munich, and I have the pleasure to be here with Bel Lazar, CEO of EPC Space. Hi, Bel. Thanks a lot for being here. How's it going?
Maurizio, always a pleasure. We see each other at many shows throughout the year,
Yes.
so it's another good time to meet and discuss about GaN.
Yeah, absolutely. Thanks for your time. So, Electronica is one of the most trade shows, most important, significant trade shows for electronics industry. What's news? Tell me more about EPC Space. What key technology are you showcasing during these days?
So we have a nice setup for EPC, where we're presenting EPC products
Yep.
and EPC Space products. We've made significant progress in the last few years, both on the commercial side and on the red hard side. On the red hard side, I'm pleased to announce that we have qualified most of our EPC 7, which is our third generation
Yep.
red hard products. And we have several discrete products from 40 to 300 volts. And then we have some red hard ICs that we have launched this year. So it's been a great, very productive year for EPC and EPC Space.
Yeah, yeah. So let's talk space. So space is a difficult environment, harsh environment, right? So
Yeah.
we have to take care about temperature, extreme temperature, vibration, vacuum conditions. So why is so difficult for electronics? So there is specific features that you have to take care with more attention for electronics, of course.
Yeah, sure. I mean, if you think about it, once a satellite is launched in space, you already get an opportunity to repair. And then sometimes the missions are 18 years. And so you have to take care of, anticipate what could go wrong, right? But the most important thing for space, it's radiation, actually.
Yep.
And the radiation environment comes in three forms. You get the gamma radiation, neutron radiation, and heavy ion bombardments. And EPC and EPC Space do extremely well. It's our radiation-hardened devices under radiation can withstand radiation and exceed all the requirements. And you got to remember, again, it's 18 years. Now you get the thermals and the mechanical fatigue would be the second most important thing. And we go through a rigorous qualification at EPC Space for all these environments. And when we produce our space product, they're intended to survive space for 18 plus years. We're not making them to survive space for 1 or 2 years. This is something for 18 years. So it's a harsh environment, but we take care, predict proactively what needs to happen, and we make sure we have devices that can survive this.
And let's talk about GaN for space. So what specific advantages GaN can offer over traditional silicon-based solution, of course? How does GaN technology contribute in terms of sustainability for space missions?
Yeah, so let's talk about the advantages of GaN over silicon for space. One, our GaN has absolutely no issues with what's called TID, or total
Yes.
ionizing dosage, because there's no oxide layer. And so our GaN devices can survive up to 40 megarads plus. Plus, we design products that actually have very high, what we call single event capabilities. So the first advantage over silicon is that a lot of time with silicon, you have to balance between TID and single event. In our case, you don't have to worry about TID. You just need to worry about single event. And we control that, and we come up with devices that can actually be very good for single event. So that's a major advantage over silicon. The second is the efficiency. We've got low RDS(on) and all kinds of, in any way you look at it, GaN is better than silicon in terms of figures of merit. And then another advantage is integration. With GaN, you can easily integrate, and so you can come up with a GaN IC a lot easier than you can come up with how you integrate actually in a silicon power FET. Another advantage is reliability. We have done tens of thousands of reliability on each type of failure mode possible, and so we have lots of reliability data. One additional advantage is actually cost and availability. Our devices, red hard devices, cost 1/3 of what a red hard silicon costs in terms of selling price, not just cost. And availability. We've got products on through our distributors, and our lead time is really short compared to that of red hard silicon. So those are the advantages.
This is important. This is
Yeah.
important. So, can you give some examples of application of GaN for space, practical applications?
Yeah, I mean, we've got, for example, like VPT makes a 400 watt DC-DC converter
Yeah.
that's used in geo environment, geo satellites.
Yes.
They were among the first ones to sell this to a geo application.
Good.
So several of our GaN devices, mainly 200 volt in that specific example. That's one. And then we've got MDA, MDA Canada. We've sold several devices that are actually flying in geo orbits.
Nice.
And then we do have OneWeb, Gen 1 satellite. We've made motor drivers, and as you might know about OneWeb satellites, there's about 600 plus satellites flying, and we make the motor drives for the reaction wheels. So those are a few examples.
Nice. So you mentioned also cost, about the cost of GaN devices. So what are the next manufacturing or the current or the next manufacturing challenges that can improve again the GaN and offer a good opportunity for space mission to make the technology more accessible?
So one advantage we have is that we leverage EPC's commercial fab setup. I myself, I'm the chief operating officer of EPC. We're using a commercial line, but we make specific designs that are red hot, and we run them on the same line. So there's no additional cost of running a red hard fab per se. If you go and establish a red hard fab, your cost is going to be very high because the volumes are low. So what we do is we run in a very high volume environment, but we make specific custom epitaxial growth, and we run them on silicon, and we use a silicon fab. So we're leveraging a high volume line to produce a low volume radiation hardness, and so cost of the fabrication is low. The other thing is at EPC Space, our products are all flip chip, which means cost of manufacturing is low, no wire bonding, which helps in reliability and driving the cost down.
And talking about reliability, so I also posted on Power Electronic News a sort of a review for the 16th report of EPC Space, the last report of EPC in this case.
Yeah,
EPC in this case. So about reliability. So what next innovation, improvements, game changer for GaN technology we need, or you would expect to further revolutionize the space mission and increase efficiency as well?
Yeah. So for example, right now on the commercial side, our Gen 7 is in the R&D mode. So we've already have 6 generations of commercial product, and we've learned a lot about this. And so we're using our experience and knowledge on the radiation hardness and leveraging the technology development by EPC to come up, make the radiation hardness at the next level. And for example, we do have, we've come down to a 10 volt for POL applications for space. It's currently in R&D. We've worked with a prime manufacturer in the United States. We've got some funding, and we've developed a low voltage. So the next development would be how do we capture more sockets that we didn't capture in the current products that we have 40 to 300 volts. And the 10 volt opens up a POL application for us. And so that's part of our new technology development.
Good, good. So let's talk about space.
And ICs, I should mention ICs.
Yes.
We're actually launched 2 radar ICs, and then we're going to launch 1 or 2 more in the next couple of years.
Okay.
So that makes our portfolio wider.
Wider.
Yeah.
Good. So, talking about space missions, so far from our planet. So let's think also about Mars and other Jupiter and so on,
Venus.
Venus and so on. So we know that the condition, the environment is harsh, probably worse than our planet. So what, in general, from technology point of view, what advancement you would expect that human at the end can reach these planets?
Yeah, I mean, just from a
Just
electronics
think Mars.
standpoint, right?
That is,
So, if you think about it, if you do like Mars, Mars would be you have to have devices that can operate in the cryogenic
yes,
type
cryogenic. Yeah.
mode. And then we probably have to modify our designs to be able to operate in a cryogenic mode. As far as like planets like Venus, where you require like extremely high temperatures,
Yeah.
we have to probably come up with some special packaging or some
Okay.
special way to handle the heat. But the good news is GaN itself as a material can handle such extremes. We just have to come up with packaging or better ways of handling it to be able to handle such extreme environments. Yeah.
GaN is ready for Venus.
It is ready for Venus and Mars. We just need to make some adaptation to it as far as packaging. Yeah.
Thank you, Bel. So my last question. So talking about exoplanets. So probably one day we can reach this exoplanet. Humanity will be able to reach this exoplanet, or we cannot. So we are condemned to stay near to our solar planet. So do you think that there are other intelligent lives, more or less? Then this is another question. So do you believe in or we are the only ones that are here?
Yeah, first of all, to get to these planets, you can't do it in today's technology, right? So you probably have to change the propulsion methods, right? You probably need because if you start, it'll take you like maybe 2-3 lifespans to get to these planets. So, but if you do, for example, change your nuclear propulsion, if you come up with a nuclear propulsion, then that cuts the time to get to these planets. And then, you'll have to figure out, in my opinion, obviously it's a prediction, that probably the first such trips would not be human. It'll be some kind of robot with intelligence, like AI. So you need an infusion of robotics and AI and a new propulsion methodology. So to launch these spacecrafts to get there. So it'll be fascinating if we could do it, right? But I believe we can. As far as other people, other people similar to ourselves that are living in different type of planets, we don't have evidence of such thing, but I believe there are, and it'll be fascinating if we can discover them. So, yeah.
Looking forward to it.
Yeah, me too.
So thanks a lot, Bel. Thank
right.
you for your time. Thank
Maurizio,
you.
always a pleasure.
My pleasure. Thank you.
Thank you. Thank you.